One, microcontrollers and microprocessors. The subject is microcontrollers and embedded systems, 6th semester. Hi there, I'm Bharath from CSE Artificial Intelligence, Sri Venkateswara College of Engineering. The subject, as I said, microcontrollers and embedded systems, and I'd be presenting on the topic of microcontrollers and microprocessors. How both are different, let us explore it. This is the first video assignment. Microcontrollers and microprocessors. First, let us understand what they are. Let us take an introduction into the subject. Microcontrollers and microprocessors form the backbone of embedded system and computing technologies. These powerful components enable the functionality of countless devices we use daily, from simple household appliances to complex industrial systems. This presentation explores their architecture, functions, application, and future trends for an engineering audience. This is about the introduction to microcontrollers and microprocessors. Now, moving further, let us go on into the next one, where is about the architecture comparison. Microprocessors and microcontrollers. Let us compare these two, how they are similar and how they are different. Microprocessors have an external memory architecture, whereas the microcontrollers have integrated memory architecture. We can see that the microprocessors have separate RAM, ROM input-output ports, whereas microcontrollers have built-in RAM, ROM and input-output ports. It has a higher processing power, and microcontrollers are optimized for specific tasks. Examples of microprocessors are Intel x86, AMD Ryzen. Examples of microcontrollers are PIC, AVR, ARM, Cortex-M, all these. And as we can see, I would like to use a laser pointer here. The different spaces of core. Here microprocessors has only CPU embedded into it. This has CPU, RAM, flash and other peripherals embedded into it. Applications of microprocessor is that it is widely used in the computer systems, and in microcontrollers it is widely used in the embedded systems. Scale, difference of scale is this is used for large scale processing, whereas this is used for small scale processing. Usage will have PC, mobile phone, Raspberry Pi, etc. All these use microprocessors. Microcontrollers are used by Arduino, SMT, MSP 32, 432, and etc. All these. The fundamental architectural difference lies in integration. Microprocessors require external components to function as a complete system, while microcontrollers package these elements into a single chip, making them ideal for dedicated applications with space constraints. This is about the comparison of architecture of a microprocessor and microcontrollers. Now let us see about the working mechanism. We have 4 points here. The working mechanism is divided into 4 steps. One is the fetch, decode, execute and store. So what happens is in fetch, the retrieve instruction from memory. In fetch means going somewhere and fetching the details or data that you need. This one goes and fetches instructions from memory, and then it interprets the instruction. What instruction you have fetched has to be decoded, and that happens using the decoder in this decode step. In the execute step, after decoding, what instruction is given, it performs the operation. Store is it writes result back to the memory. These are the 4 steps of working mechanism of a microcontroller and microprocessor. Both these microcontroller and microprocessor operate using the fetch, decode, execute, store cycle. The CPU fetches instructions from memory, decodes them to determine the required operation, execute the instruction using arithmetic logical unit, and stores the results back in memory or registers. This cycle repeats millions of times per second, enabling complex computation and control of functions. This is how the microcontroller and microprocessor works. In the next one, applications and use cases. Let us look at different applications and use cases, each specifically. The first one, microcontroller applications are, it is used in embedded systems, it is used in automotive control systems, IoT sensors and devices, medical devices like insulin pumps and pacemakers, and consumer electronics like remote control and toys. Microprocessor application, personal computers and workstations, servers and data center, gaming consoles, high-end smartphones and tablets, scientific computation, computing and simulations. These are the applications of microprocessors. Next, the choice between microcontroller and microprocessor depends on application requirements. Microcontrollers excel in Microcontrollers excel in dedicated real-time control application where power efficiency and reliability are crucial. Microprocessors are preferred for applications requiring significant computational power and flexibility for diverse tasks. Let us now move on to the next one. In this, we are going to check on the performance and efficiency of these two microcontrollers and microprocessors. First thing is about the clock speed. 8 megahertz to 400 megahertz microcontrollers. Microprocessors are for 1 gigahertz to 5 plus gigahertz. Power consumption has a low power consumption. This is a high one. Memory is KB to MB range, but this is in the GB range. And cost 0.5 to $10, but here it's about $50 to $500 microprocessors. So microcontrollers are cheaper than microprocessors. And real-time response is excellent in microcontrollers but variable in microprocessors. Here, microcontrollers prioritize efficiency and deterministic behavior, making them ideal for battery-powered devices and real-time applications. Microprocessors offer substantially higher processing capabilities at the cost of increased power consumption, making them suitable for computationally intensive tasks where power constraints are less critical. The next one we'll move into on the next slide. Programming and development. What are the languages required for microcontrollers? That is C, C++, and assembly. As you can see the laser pointer. Microprocessors C, C++, Java, Python, etc. Development tools, IDEs, Arduino, IDE, MPLAB, Kale are used. Debuggers, JTAG, SWD interfaces. Frameworks are used. Programming microcontrollers typically involves working closer to the hardware level with careful consideration of memory constraints and timing requirements. Development environments range from manufacturer-specific tools to open-source platforms like Arduino that abstract hardware capabilities, complexities. Microprocessor programming offers more flexibility but may require understanding of operating systems and complex software stacks. The next slide is about the future trends and advancements of these uh, systems. AI and machine learning, edge AI processors and neural processing units are used. RISC-V architecture, open source hardware revolution, ultra-low power computing, energy harvesting microcontrollers, neuromorphic computing, that is brain-inspired computing architectures. The future of microcontrollers and microprocessors is evolving toward a greater integration of AI capabilities. Open architecture like RISC-V and dramatically improved energy efficiency. Neuromorphic computing promises to revolutionize how processors handle complex pattern recognition tasks by mimicking neural structures. These advancements will enable new applications in edge computing, autonomous systems, and ultra-low power IoT devices. This is about the future trends and advancements. Case studies and real-world examples. Arduino, that is ABR microcontrollers, power countless maker projects, powers countless maker projects, educational platforms, and prototypes with its accessible development environment and extensive community support. Raspberry Pi, which is the ARM processor, bridges the gap between microcontrollers and full computers, enabling affordable computing for education, hobbyists, and industrial applications. Smartphones, which is ARM Cortex, utilizes powerful ARM-based SoCs that combine microprocessor cores with specialized accelerators for graphics, AI, and signal processing. These real-world implementations demonstrate how microcontrollers and microprocessors have transformed various industries. The Arduino platform revolutionized prototyping with its AVR microcontrollers, while ARM's architecture dominates mobile computing. Industrial automation relies heavily on specialized microcontrollers for reliable real-time control of critical systems. These were the case studies and real-world examples. Now we'll move on to the conclusion. By now, what all we have seen, let us look at 4 points now. Complementary technology, application-driven selection, converging evolution, and foundational impact. Microcontrollers and microprocessors serve different but equally important roles in the computing ecosystem. Choosing between them depends on specific requirements for power, performance, cost, and functionality. Converging evolution is the line between microcontrollers and microprocessors continue to blur with SoCs and heterogeneous computing. These technologies form the foundation of modern digital transformation across all industries. Microcontrollers and microprocessors have revolutionized how we interact with technology and will continue to drive innovation across industries. As we move towards more connected, intelligent systems, understanding the strengths and application of these fundamental concepts become increasingly valuable for engineering and developers. Their ongoing evolution promises to enable new solutions to complex challenges in energy efficiency, computing power, and intelligent automation. These are the conclusion. Thank you very much for being a part of the video. Let us meet soon in the next one. See you soon. Thank you.